Right, these are the pendulum notes that go along with our simple harmonic motion notes. Oh. And they are on the back in the pendulum square. You will need to leave space for two different topics. Those two different topics will be restoring force and period of a pendulum that will go in that square, as well as we'll do two examples in the example square. So a pendulum is like the object to the left. It is usually a mass, and that mass is called a bob that hangs at the end of a string. It could be some sort of mass at the end of a pipe or end of chains, kind of like the swing set in the playground. That swing is a pendulum, and it just literally has plastic attached to the end of chains. Okay, I recommend drawing this picture because gravity supplies the restoring force to create simple harmonic motion. So this restoring force is actually a portion of this weight force, and it pulls it down and back towards the middle. So it creates that restoring force which pulls it to equilibrium, which is our definition of simple harmonic motion. As the pendulum goes higher, gravity will act more on the pendulum to pull it back, so that restoring force will go up. All right? So the restoring force for a pendulum is the component of the gravity that is tangent to its circular motion. So this piece is the same as this piece. And if you notice, the F of G is the hypotenuse of this little triangle turned on its side. And then the F of T would be this value right here that's the adjacent. And this F of R would be our opposite. So if we use sine theta and we say that opposite is the F of R and the hypotenuse is the F of G, then we can rearrange that equation to say F of G is mass times gravity times the sine of theta, and that will allow us to solve for our F of R. So you need to have this formula, as well as I would go ahead and label this drawing accordingly. Now, what restoring force does gravity supply to a 0.5 kilogram pendulum that's at 30 degrees? Well, our variables are 0.5 kilograms, and our angle is 30 degrees. So we could use our formula we just had, which is F equals mg sine theta. And we could multiply those three numbers together because we know gravity here on Earth is 10 meters per second squared. We also might have to double check that our calculator is in degree mode by doing home 5-2, and make sure that you set it in degree mode and make it the default if it's not, but then you could do this calculation and come up with 2.5 newtons. The next question would be is what is the restoring force if I take it to 90 degrees instead? Okay, well 90 degrees is a bigger angle, and so that restoring force should go up according to what we said earlier. And so if we do that calculation again, we find out that yes, it does go up because the sine of 90 is just 1, and so then it's 1 times the mass times gravity. So my picture over here shows that at a 90 degree angle, the F of G is the restoring force and it's going straight down. So just mass times gravity really is the actual answer on that one. Okay, there's a video here of a swing. It's a pendulum swing, and they're launching off of it into a lake. It's kind of a cool video. I'm not going to play it in the recording because that would violate some copyright rules, but I would just, if you want to copy that, or if you want to write that down and go to that site and look at that video, it's really a cool video. Okay, so the next piece that we're going to talk about is going to be the period of a pendulum, and it's given by the formula of T equals 2 pi square root of L over G, where L is the length of the period, and it's in meters. G is the acceleration due to gravity, which is in meters per second squared, and T is the period in seconds. So this allows us to calculate period, and period is, remember, the amount of time for one swing. And so if we're talking about the amount of or swing, then when we're talking about that, it swings to the bottom, and then it swings over here, and then it'll swing back. That is a complete cycle. So the amount of time it takes to do that entire thing would be the period. Okay. Also, we have some manipulations of this equation that might help. So if we want to solve for the length, if we knew period and gravity, then that would be t over 2 pi squared multiplied by g. If we want to solve for g, that would be L divided by t over 2 pi squared. Now the pi button on your calculator is next to the H button in the alpha area. That's where I want you to use the pi button. Also, you need to be aware that it is a division sometimes, and when you divide it, you have to divide by 2 and divide by pi. So just make sure that you do that when you're doing calculations. Okay? So there are also some important things to notice. Notice there's no mass in that equation, so the mass does not matter, or the period doesn't depend on the mass. It could be a huge wrecking ball, or it could be a little wiffle ball. It doesn't matter. The period swing is going to be the same amount of time. Then the length and the gravity are the only two variables that are in the formula, and they're the only two variables that affect the period as well. And then as the length of the pendulum becomes longer, the period also becomes longer. So it's important to realize that as that L is longer, because it's on top of the fraction, it's going to directly affect that period. So as one goes up, the other goes up. Now it's not going to be an exact relationship, but it will make it longer. So I have a grandfather clock here in Montgomery that has a period of 1 second per swing. I want to know how long the pendulum is for this to happen. So I know that the period is 1 second, and I know gravity is 10 meters per second squared, and I'm looking for the length. So I know my original formula is t equals 2 pi square root of L over g. I gave you the manipulation by first dividing by 2 pi, and then we have to square to get rid of the square root. So we have to square the whole t divided by 2 pi expression. And then we'll have to multiply by g to get L by itself. When I type this in the calculator, I type 1 second divided by 2 divided by pi. And then I hit enter. And then I square it. And then I multiply by 10. That way I don't have to worry about doing the whole double sets of parentheses and all those kind of things. So be careful and make sure that your pi is on the bottom and underneath the 1 second, not on the top and multiplied. So be careful about that. So make sure that everybody's typing it in their calculator, because this is the biggest mistake that gets made, is how it's entered into the calculator. And then you should get 0.25 meters. Again, check with your neighbors if you're and how they're calculating it. If you're struggling, if not, you can bring it to me when I'm available. All right. This concludes this portion of the notes.